Welcome to AP Calculus. We are reviewing the 4.5 handout. First page is review. When it comes to tangent x, we derived it 2 days ago. But there is a mnemonic device which we did not learn. When we did a u substitution, it came out to negative natural log of the absolute value of cosine x plus a constant of integration. How many of you would be interested in learning the mnemonic device for the antiderivative of tangent x? Anyone interested? I see widespread requests. This one is just weird enough to be memorable. It's entitled The Four Ofs. When I say go, you're going to say out loud and in unison the opposite of, the natural log of, the absolute value of, the cosine of x plus c. That's what makes this one memorable. There's four ofs. So when I say go, say the opposite of, the natural log of, the absolute value of, the cosine of x plus c. Here we go. Ready? Go. The opposite of. Wait, oh, hold on. You have to emphasize the ofs. That's what makes it memorable. Ready? Go. The opposite of, natural log of, absolute value of, the cosine of x plus c. It's the four ofs. We learned for secant, that has not a chant, but a story. Derivative is secant x tangent x. The antiderivative, we multiplied by 1 in the form, what form of the number 1? For those of you who forget this on next Tuesday's quiz, and you have to re-derive it, you just go in your imagination to a dark and stormy night, 3:30 in the morning, candles on. What form of the number 1? By what form of the number 1 do we multiply secant x? Does anyone recall? Elon, do you know?
Is it like sine x over sine x?
No. It's not 5 over 5. Neither is it 12 over 12. Will, do you remember? That's it. It somehow popped into your mind. It was secant x plus tangent x over secant x plus tangent x. So if you let u equal secant x plus tangent x, it's 1 over u. So it comes out to be the natural log of the absolute value of secant x plus tangent x plus a constant of integration. Nice work. By the way, for cosecant, piggyback off of secant, just make it negative cosecant x cotangent x. Likewise, here for cosecant, piggyback off of secant, make it negative natural log of the absolute value of cosecant x plus cotangent x plus c. For 9, cotangent piggybacks off of tangent, make it negative cosecant squared x. And this cotangent piggybacks off of that tangent to make it positive natural log of the absolute value of sine of x plus a constant of integration. And the last one I asked you to do today was 1/2 x to the negative 1/2. Of course, that can also be written as 1 over 2 radical x. And this guy over here, x to the 1/2, that would be x to the 3/2 over 3/2, so we're talking 2/3. X to the 3/2 plus c. By the way, up here on x to the n, if you forgot to restrict the n value to anything but -1, then that's not full credit. The antiderivative of x to the n is x to the n plus 1 over n plus 1 plus c, semicolon, n cannot equal -1. Because when n does equal -1, what's the antiderivative of x to the -1? Oh, x to the -1. That's, I better save this. X to the -1 is 1 over x. What's the antiderivative of 1 over x? A little bit louder. Thanks, Will. Will's on fleek. Natural log of the absolute value of x plus c. It's Will's day. You're an AP Calc. You knew it would come. Oh, hey, you know what? I'm responsible for letting you know that there's 2 alternate forms for which you are going to be held accountable. The four ofs, because of the properties of logarithms, that negative sign can come up front as an exponent. Cosine x to the -1, that's 1 over cosine is secant. So sometimes the antiderivative of tangent x is written as positive natural log of the absolute value of secant x plus c. Likewise, same thing for cotangent. Since sine x is cosecant x to the -1, sometimes cotangent in a true-false setting, you'd have to say that this is true. It's negative natural log of the absolute value of cosecant x plus c. So notice how these have that opposite relationship. Natural log of absolute value secant, negative natural log of absolute value cosecant. So this is no surprise, but those alternate forms are forms for which you are responsible. Any follow-up questions on the review? Now tuck this packet away. It's the notes for class tomorrow. We just got a head start because we don't want to take too much time reviewing at the beginning of class tomorrow. Tomorrow's fundamental theorem of calculus day with a little bit of review planned at the beginning. Okay, today is 4.4 day, although I do realize that you probably have a question on the last problem on the homework due today. When you take a look at homework 4.3, the homework due today, in my fourth period class, they asked about number 57. And the basic question on number 57 is, isn't there a shorter way? How many of you are wondering if there's a shorter way to do the last problem on the homework? Yeah, I don't know of one. But keep in mind, as you saw in the AP, you have an AP test right in front of you, or you had it minutes ago. Believe me, they don't ask you things that take this much time. This is just more of an attention to detail. Do you have the perseverance that it takes to have high quality character? Do you have perseverance? That's all this was about. They would never put something like this on the AP test, so you can relax. But all the details are there. It takes 20 minutes. They don't give you problems that take 20 minutes to find one antiderivative. Any questions on the homework due today? I'm just going to pause while we collect these questions up.
Well, where do you got u squared plus 2u plus 1 minus 4?
So u squared plus 2u plus 1 minus 4. Right here? What's your question?
Like how do
I mean, how to get from the one above it to this one?
Yeah.
Yeah, u plus 1 squared, when you expand that, it's u squared plus 2u plus 1. This is used in the FOIL method. And I also, you've got the, I also factored out a 1/4.
and then it, okay.
So I first of all factored out a 1/4, which brought a 1/4 here, and then so this was a 1, and that was a 4. So that's why that 4/4 became a 4. Further questions on the homework due today? All right, homework 4.4 is a problem that I'm going to announce at the end of class today. It's to be done on paper. Homework 4.4 is paper submission. Riemann sums look like rectangles that are added up. It looks like a curve broken up into rectangles. They're used in the real world to communicate. Statistics is one place. Here's increase in deadly vehicle crashes. They used what appears to be a set of rectangles. It kind of looks like it could be the areas of these rectangles could be the area under the curve. Welcome. Go on in. So today's lesson will look like an area under a curve divided into rectangles. This, by the way, this set of rectangles represented an increase. I mean, they wanted to do a story on an increase in deadly vehicle crashes. Apparently in the year 2016, deadly vehicle crashes accounted for about 37,000 fatalities in thousands. That's in thousands. So it's 37 million. It can't be 37 million. Fatalities in, that's fatalities in thousands. Here, this is 50,000. I was going to say, we don't have 37 million people dying on the roads in 2016, maybe 37,000, and sure enough. These numbers are in thousands. These are actually explicit in ones. Those are in ones. So today's lesson will look like a whole bunch of rectangles under a curve. Now, what's going on with Riemann sums? This is a major concept development lesson. And the concepts we've developed so far in this course are the limit, the derivative. We've seen the antiderivative, but today we're going to look at the integral. So let's begin. going to be a lot of detail in this lesson. And that's why I want to emphasize that you're more than welcome to move around the room in case you need to see what's going on. Now, there is one document that I need before we go any further. See if I can locate that. Homework 4.4 is due tomorrow. Homework 4.4, the topic is Riemann sums. So, on student supplied paper, oh, and Jack and Will, go ahead and table your conversation, please. It's going to take a lot of concentration. So, Riemann, spelled R-A-E-M-A-N-N. And Riemann did a lot of work to defend the truth of Newton's calculus. He died at age 39 of tuberculosis. In his short life, he made a big difference in the mathematical community. Riemann sums used to approximate total distance traveled. That's the real world context we're going to use. Now, you can also use Riemann sums to approximate displacement, but we're going to focus today on the real world problem of total distance traveled. And you might notice that the first problem that we did not do today on the AP test, problem 6, was find the total distance traveled. So we're going to, in a matter of days, we're going to know how to do problems 6 through 10 from that same AP test. So here we go. First of all, when it comes to a Riemann sum, you may as well know that the real world situation in which we're going to be learning about this, basically we're going to start with, and this is my teaching philosophy, is to start in the RW, the real world. Because when students see how calculus is connected to the real world, their imagination is more likely to engage. So I want to fit to height briefly and then fit to width so we can see the whole thing. So my wife used to have a job in downtown Chicago where she would have to commute in every morning. Let's say that V represents her velocity in miles per hour to the vehicle that she drives into Chicago, and let T represent time. We're going to put time in minutes. Sometimes when there's a lot of snow outside, commute times are measured in hours, but when there's not too much snow, commuting times are measured in minutes. And let's locate her velocity. Let's check her velocity every 10 minutes, 10, 20, 30. Suppose she arrives in the loop 40 minutes later. And her velocity starts out at 30 miles per hour. And she's going faster there for a while. I mean, it varies with time. Going faster, coming down, slow, faster again, slow, and then by the time she hits 40 minutes, she is at 28 miles an hour. This is the point 40, 28. What is the total distance traveled? Well, to find out, we can set up either a right-hand Riemann sum, a left-hand Riemann sum, a midpoint Riemann sum, but there's also something called an upper Riemann sum and a lower Riemann sum. And the truth is, just like there's an infinite number of ways to represent the number 1, 2 ways that come to mind are 5/5 and 12/12. Another way that comes to mind is secant x plus tangent x over secant x plus tangent x. In the same way there's an infinite number of ways to represent the number 1, there's also an infinite number of variations on the Riemann sum. These are just the 5 that are called for most often on the AP test. What would it look like if we were to construct a right-hand Riemann sum, which I'll do in red? For a right-hand Riemann sum, we're going to take and specify the number of rectangles as 4 rectangles. that graph of the number of vehicle or fatalities in vehicles had a lot more than 4 rectangles. I didn't even count how many rectangles it had, but it had a rectangle for every year from 1975 up to the year 2016. That's way more than 4 rectangles. We're only going to use 4 rectangles in this one. And let's draw them using golf balls in red, a right-hand Riemann sum. If I'm going to go with 4 rectangles, then I want to divide the time from 0 to 40 minutes into 4 intervals. Sometimes the intervals are equal amounts of time, but other times you'll have like 12 minutes in the first interval, 3 minutes in the second interval, etc. So let's start out with equal amounts of time. If it's a right-hand Riemann sum, then the first interval, 0 to 10 minutes, we take the rightmost time. We take the time on the right, 10. Let's call that C1. That's golf ball 1. And label C2, 30 minutes is going to be golf ball C3. And for the uninitiated, for those of you who just stumbled across my YouTube channel, the golf ball is just a metaphor to represent the input to a function or a value of x. Now, suppose it is known that at 10 minutes, my wife's vehicle is traveling that's going to be the point 10, comma 58. She's traveling 58 miles an hour at the instant that she's 10 minutes into her commute. Now, what we do is, on the homework that you're doing tomorrow, you're going to set up the golf balls on the ground, but you're also going to show the golf balls clearly visible in the air, and then use that golf ball height to draw a rectangle. This is the first rectangle in this Riemann sum. Now, suppose that 20 minutes into the commute, golf ball 20 goes up to the point 20, comma 50. So 20 minutes into the commute, she's traveling 50 miles an hour. Let's draw a rectangle that's 10 minutes wide by 20 miles per hour, excuse me, by 50 miles per hour tall. The third golf ball goes way up here to 70 miles an hour. So when she's 30 minutes into the commute, she's traveling 70 miles an hour. Let's draw a rectangle that is 10 minutes wide and 70 miles per hour tall. This one hangs out above the curve quite a bit. And then finally, the fourth golf ball goes up to a height of 28. Make golf ball C4 visible on the ground and in the air. So here we have the fourth rectangle. And what does this have to do with the total distance that my wife drives on her commute into work? Well, there's a very basic idea here that you learned in elementary school. Distance equals rate times time. If you want to find out the distance someone traveled, find their rate and find their time. So, Crystal, how many hours is this? That's right, it's 1/6 of an hour. Each 10 minutes is a 1/6 of an hour. So each one of these, we have to convert to hours because we want distance equals rate times time. The rate is 58 miles per hour times 1/6 of an hour. Rate times time. The area of this rectangle will give us the distance traveled during the first 10 minutes, approximately. It's going to be an overestimate because the area under this curve would be exact. It would be velocity times time. It would be the exact distance. We're approximating the distance that she travels in the first 10 minutes by finding the area of this rectangle. So, each one of these rectangles is 1/6 of an hour wide. And so if you want to calculate the total distance traveled, here's what I'd like you to do. I'd like you to say that the approximate total distance is, and sure, I can write this as 1/6, the area, basically it's area 1 plus area rectangle 2 plus area rectangle 3 plus area rectangle 4. So, we're going to call it, in fact, I'm going to keep everything in orange because we're going to use a different color for the rest of that. We're going to go orange. So, using a right-hand Riemann sum, we get 1/6 times, how high is this rectangle? It goes up to 58. 1/6 times 58 plus 1/6 times, how high is the second? Oh yeah, that went up to 58. This one went up to 50. So 1/6 times 50 plus width times height is 1/6 times 70 plus 1/6 times 28. Now, what we end up doing on these, we always factor, if it's the same number, if it's the same width, we just factor out the 1/6. So there's not much to this. Just factor out the 1/6. You get 58 plus 50. You might even be able to do this in your head. Plus 70 plus 28. What is that? It's 120, 178, 88, 98, 208, 206. So it's 206 divided by 6. Now, I don't know offhand what 206 divided by 6 is. Take out your calculator, type in 206 divided by 6. Got to be close to it. What did you get when you took 206 divided by 6 on your calculator? In decimal form, it comes out to what? Just call it out. We'll keep things moving along here.
34.33.
So 34.333 repeating?
Yeah.
Okay, so 34 and a third miles. You can't just write 34 and a third. 34.13. 34 and a third. We don't mix decimals and fractions. So it's 34 and a third miles. My daughter and I ran the Hot Cider Hustle in Chicago last weekend, and it's supposed to be an 8K race, which is about 4.97 miles. I didn't know whether they had signs, like we were running for a while, there was a sign that said 1. I think, well, if that's 1 kilometer or 1 mile. It was advertised as an 8K race, something else might be 1 kilometer. 2, 3, then we see a sign that says 4. I was at 4. I usually stretch after running for about a mile, so it's like, you know what? Looks like we're about halfway done, 4 kilometers done. And then we've been running for a while, so I'm thinking, I'll just talk to my daughter. Hey, sweetie, I think I'll just stop and stretch. You can go ahead. I'll catch up to you. There's a lot of noise. People are starting to run really fast. It wasn't 4 kilometers. It was 4 miles. It was 150 yards from the finish line when I decided to stop and stretch. My daughter ended up beating me by 10 seconds. I couldn't quite catch up to her. It's like, what's going on? It was 4 miles. It wasn't 4 kilometers. But I had her chip because she got really hot. It was a cold morning, but then she got hot while she was running. So I had her chip with my chip, so her finish time was the same as mine. So, but she actually did beat me. What for? For what? Don't say 34 and a third. Say 40 and a third miles, not kilometers, not feet. Attend to precision and pay attention to units. Okay, now that's what a right-hand Riemann sum looks like. In blue, we're going to go left-hand Riemann sum. Had this been a left-hand Riemann sum, the approximation would be a little bit different. For a left-hand Riemann sum, instead of the right-hand golf ball on each interval, let's take the 4 intervals and take the leftmost golf ball. So please label C1 at 0. C2 is going to be 10 minutes. C3, C4. And so golf ball C1 goes up to 30. Draw the rectangle. Draw the second rectangle. The first rectangle is 1/6 by 30. What are the dimensions of the second rectangle? Shiara, go ahead. 1/6 by what? How high is golf ball C2? No. What is the velocity at time 10 minutes? 58. So golf ball 2 is up to 58. Okay, so draw that rectangle. The third rectangle, golf ball C3, goes up to 50. Golf ball C4 goes up to 70. So a left-hand Riemann sum would give you a different approximation. It would be 1/6 times the quantity, 30, plus 58, plus 50, plus 70. Slightly different approximation. There's also something called a midpoint Riemann sum. Now, at some point your diagram gets really busy, so you may want to just sit back and watch instead of trying to draw all of them. But if you were to draw the 4 rectangles of a midpoint Riemann sum, you would take the middle golf ball. You would take the 5-minute golf ball, 15, 25, and 35. Send these golf balls up to the curve. I don't know what that number is, but then you would draw a rectangle that's 1/6 of an hour wide, and it looks like this is somewhere around, maybe 49 miles an hour. Golf ball at 15 minutes, the velocity is right here, so you would draw a 1/6 by whatever that velocity is. There's a midpoint rectangle, and then take this 35 minutes. What was her velocity at 35 minutes? I don't know, but so the sum of the areas of those 4 green rectangles would give you a midpoint Riemann sum. There's also a an upper Riemann sum, lower Riemann sum. Since these 5 are used quite a bit on the AP test, I want to tell you what an upper Riemann sum is, without necessarily polluting my diagram with too much busyness. An upper Riemann sum would be the highest golf ball in the 10-minute interval. So take it's up at the upper end. So this, I'll bet the upper would be right here, the highest golf ball. Here in this 3rd interval, it looks like that's the highest one right there. And then here, that's the highest one. So that would make sure that you don't underestimate the total distance. It's the upper Riemann sum is the highest of all the golf balls. By the way, I start using golf balls in math education welcome, Wesley, glad you could make it.
Part of the choir festival cleanup crew. That is the reason for my lateness.
Thank you for your service. I start using golf balls in Algebra 1. The whole reason the golf ball thing started was because of Riemann sums. It's to be able to visualize left, right, midpoint, upper, and lower Riemann sums. You don't tell the people that in Algebra 1, but that's why it's happening. I don't know what other color, maybe black. A lower Riemann sum would be, just look at all the golf balls in the first 10 minutes. Whatever the lowest one is, that's where you draw your rectangle, black. So a lower Riemann sum would be the lowest of all the golf balls on the interval. Looks like it might be close, it might be this one right over here. In a lower Riemann sum, you take the lowest option for every 10 minutes, it'd be right here. So that's if you want to make sure that you underestimate your answer. So there's 5 types of Riemann sums you're responsible for: right, left, midpoint, upper, and lower, but there's many more. Like you could say, well, let's take the first minute into the interval. Let's take the golf ball at 1 minute, 11 minutes, 21, and 31 minutes. That's where we're going to get our rectangle. Shriana.
Which one will give you the most accurate answer?
Well, it depends on whether the function is increasing or decreasing. We're going to do several more examples today where you're going to get a feel for if you do want accurate. And for some curves, left-hand Riemann sum gives you the most accurate. But midpoint is often, I mean, if you just had to pick one, hoping that'll be the best, midpoint often works the best, because the midpoint Riemann sum, see this green one?
Yeah.
It's got a little bit of overhang, a little bit of underhang. It often balances things out if you go in the middle. Yes, go ahead.
So is the midpoint according to the x-axis, not the y-axis? Or the
It's a
x-axis?
midpoint, not the middle height,
Yeah.
but the middle on the x-axis.
Okay.
Okay? So now let's take a look at what the homework's going to look like. We're going to do one example that represents what you're going to have to do on the homework. Now, this next example is going to require a full sheet of 8.5 by 11 inch paper, 8.5 inches wide, 11 inches tall, and it won't fit onto half a sheet. This is a full sheet activity. There's going to be a little bit of section of given information on the top, and then 3 columns. We're going to do a left-hand Riemann sum, a midpoint Riemann sum, and a right-hand Riemann sum in those 3 columns. I'm going to show you just exactly what the expectations are. We are developing the concept for what's called the definite integral. Like if you wanted to find the definite integral from 0 to 2/3 of an hour, 40 minutes is 2/3 of an hour. Velocity times time, rate times time, total distance. As long as velocity does not go negative, total distance is the definite integral from 0 minutes to 40 minutes, which is 2/3 of an hour. v of t dt. We're going to learn how to use a Riemann sum to approximate total distance. So, by the time you walk out of here, in fact, for the homework, I'm going to give you a 3-column problem. You'll be able to complete the homework on one sheet of paper. There'll be some givens at the top, and you're going to divide your homework paper into 3 columns. You're going to have a left-hand Riemann sum on the left, midpoint, and a right-hand Riemann sum on the right. It'll just be one problem for the homework, done 3 times, and then checked on the calculator. So here we go. Get ready on a completely blank sheet of paper to put your givens on the top, and then we'll do our Riemann sums in 3 columns. So now for the givens, that's tomorrow's problem that somehow popped up there. A little scary. Here's the given information. In this case, the velocity function is going to be given as the square root of x plus 3 miles per hour. That's how fast you're traveling on your way to the city. X represents time in hours. And we're going to restrict this to x is an element of the set 2, 4. We're only going from hour 2 to hour 4. Maybe it's like from 2 p.m. to 4 p.m. And suppose that f of x is velocity measured in miles per hour. So this expression is going to be in miles per hour. And 2 and 4, those are values of time measured in hours. So we won't have to convert from minutes to hours. It'll be a little more straightforward this time. Okay, it's also given that we're going to have to find a left, midpoint, and right Riemann sum using n equals 8 rectangles. And in this homework problem, all the rectangles will have the same width. Tomorrow at the beginning of class, we're going to do a Riemann sum problem where the rectangles have different widths. I know some of you are squinting a little bit. There's one thing I might be able to do to help. I'm using gray as my color. Why don't we just go black? Might be a little easier to see. Is that easier to see? Thought so. All right. So that's a given information on the top section of your paper. Now let's go into 3 columns. So let's go to this is now going to be the left-hand column, and the left column, you don't have to write left column, I'm just doing this for note-taking purposes. Okay, in the left-hand third of your paper, go ahead and divide it evenly. Go ahead and put lines down. You don't have to fold it. I mean, if you want to, you can, but just draw the lines. Here's what you need to fit into your left-hand column. Okay. We're going to have steps that are calculated across all 3 columns. So instead of doing one problem and then doing the middle column, and then we're going to do all 3 problems top to bottom. So in the left-hand Riemann sum, let's draw a picture of what we're talking about. This will take up maybe 3 or 4 inches at the top of the left-hand column. And let's label these axes X and Y. And please put a break in the axis for space, because you have to fit so much onto the sheet of paper. Please put a break symbol. It looks like this. Because we want to start right out at 2 and go all the way to 4. Let's use as much of our space as we can so that our sketches are not scrunched. Lots of detail here. If you need to move to a different location in the room so you can see this, feel free to do that. You can come as close as you want. Now, the function square root of x plus 3 is the square root of x graph shifted 3 units up. So draw the graph of f of x right here, square root of x plus 3. Now, in section 1, we're going to have to write the c sub i's. The c sub i's are the numbers on the 8 golf balls. But we're not going to have to write down all 8 numbers. We write the first golf ball number, the second golf ball number, and the 8th golf ball number. So it's first one, comma, second one, comma, dot, 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 comma, last one. In section 2, we calculate how far apart are the golf balls. So before we finish section 1, let's go to section 2. By the way, the theme of section 1 is to come up with a graph of the situation. The theme of section 2 is to come up with the rectangle width. All 8 rectangles are going to have a width that we calculate here in section 2. And let me just see if this is showing up on my camera right there. Okay. So here's what we do in section 2. The width of the ith rectangle is going to be represented by W sub I. I is going to go from 1 to 8 because we have 8 rectangles. On the homework, you're going to have 32 rectangles in your Riemann sum. Once again, that's 32 rectangles in your Riemann sum. Today, in this example, we're just doing 8 rectangles. But the ith width, which, by the way, we represent with the symbol delta x, is always going to be b minus a over n. Which in this case, b is 4. We're going from 2 to 4. So it's 4 minus 2 divided by 8. That's 2 eighths or 1/4. So every rectangle is a quarter of a unit wide. So now we go 3. Now we know how wide the rectangles are. Sure enough, if we go by quarters, we'll have 8 sections. 2 1/4, 2 1/2. Okay, so there we have it. We only have to draw 3 of the 8 rectangles, though. Since this is a left-hand Riemann sum, we're going to put the first golf ball, make it clearly visible, just like a clearly visible axis point or a clearly visible terminal point. Here's C1. And then the next golf ball is going to be a quarter of a unit beyond that. Here's golf ball C2. Then put dot, dot, dot. And since I'm picking the left-hand side of each interval, C sub 8, the 8th golf ball, is at 3.75. Because in a left-hand Riemann sum, you take every interval of length of what delta x, which happens to be a quarter of a unit wide, and you pick the leftmost golf ball on that interval. So now we go to the curve. Make the golf ball, it's like the golf ball machine comes by, and now it's hovering in midair. So the first rectangle, the first of 8 rectangles looks like this. Golf ball C2 goes to the curve, and it's hovering in midair right there. It's a quarter of a unit wide. There it is. First rectangle, second rectangle, dot, dot, dot. Now here's the 8th rectangle. Right, so that one went crooked. So what I'm going to do is pick white, and we're just going to pretend that didn't happen. And now back to magenta. And I'm going to draw a little more carefully here. It's purple, so we're going to go to magenta. And there's golf ball number 8, suspended in midair, hanging out a little bit below the curve. So now you can tell this is an underestimate. Now, the C sub i's are the numbers on the 8 golf balls. The first golf ball is golf ball number 2. Can someone tell me what number is on the second golf ball, which is another way of asking what's the second input to the function? Take a volunteer for this. The first golf ball is at 2. Where's the second one? 2.25 is correct. So 2, comma, 2.25, comma, dot, 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 comma. The last golf ball is 0.25 to the left of 4, which is 3.75. So to calculate this, you're going to need to know the first golf ball, the second golf ball, and the last golf ball. Okay, that's sections 1 and 2. Now, let's do sections 1 and 2 for the midpoint Riemann sum. The midpoint Riemann sum, now move over to your second column, is going to have a picture that looks similar to that, but in section 1, you're going to have a break, starting with the number 2, going out to 4 and stopping. The curve is the same. The curve is, square root of x plus 3, but this time, and, oh, by the way, for W sub I, that's going to be the same, absolutely same calculation. So you can just write the word same for step 2. So it's going to be 1/4, so mark it off by 1/4. 3, 3 1/4, 3 1/2, 3 3/4, 4. Okay, but this time, instead of the left-hand golf ball, we're going to go ahead and mark the midpoint golf ball. This is a midpoint Riemann sum, so label C1 as halfway between 2 and 2 1/4. C2 is halfway between 2 1/4, 2 1/2. And then dot, 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 C sub 8. The 8th golf ball is halfway between 3.75 and 4. This time, we can mark our C sub i's as, and it's important to work with fractions, not decimals. You've got to be exact. So, I would think of golf ball C1 as 2 plus, again, the ith width is 1/4. So I've got to go 1/2 of 1/4 out from 2. So C1 is really 2 plus 1/8. Do you agree that the first golf ball is 2 1/8, or 2 plus 1/8? Comma, the second golf ball is 2 plus, by the way, 1/4 is the same thing as 2/8. So it's 1, 2 plus 3/8, comma, dot, dot, dot. Who can give me an expression using either a plus sign or a minus sign for the 8th golf ball? For the 8th golf ball in this midpoint Riemann sum. Shriana, do you have that?
Yeah, 4 minus 1.
4 minus 1/8. So the 8th golf ball is 4 minus 1/8. So when you put these golf balls in there, don't use a solid line. Use a dotted line because you want the solid line to be on the outline of the rectangle. So that's the first midpoint rectangle. Yes, go ahead.
Can I do 3 plus 7?
Now, do it with a minus sign here. And believe me, when we're going to have to reverse engineer these later on in the course. We go to this a lot. And so use a minus sign. So you don't have to draw 8 rectangles. Draw the first rectangle, the second rectangle, and the last rectangle. Midpoints have solid around the edge, so there it is. So we can visualize taking the area under the curve, dividing it into 8. Now let's go to the right column. I want you to do sections 1 and 2 for the right-hand Riemann sum. I'm going to tour the room to see how that turns out. I'm going to hit the camera here for a second, pause it, work on the right-hand Riemann sum sections 1 and 2. Right-hand Riemann sum, section 1. Oh, I forgot the break. Break in the graph so we can start right away. 2. So we've got 3 square root of x plus 3. This time, the 3 golf balls that you picked should be at the far right-hand interval, C1, C2, and C sub 8. So we've got, these are hanging out above, so we can tell this is going to be an overestimate. So I think clearly in the answer to Shriana's question, that midpoint Riemann sum is going to be the best one, the most accurate one for this. We're going to show that on the calculator. You are required to give the C sum, part of step 1 is to list out all the golf ball numbers in list form. So the first golf ball number is basically, you could say 2 plus 1/8. The second golf ball is 2 plus 3/8. Did I do that right? Let's see. 2, yep. You know what? No. 2 1/4. It's not 2 1/8, it's 2 1/4. I knew something was wrong. So the first golf ball is not 2 1/8. The first golf ball is 2 1/4. Now, if you said on your homework, look, I know what 2 1/4 is. It's 2.25. That's fine. I'll give you full credit. And then add 1/4 onto that. It's going to be 2.5, comma, dot, 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 comma, 8 is the last one. So that's totally fine if you break into decimals when the decimals are exact. 1/8.125. Yeah, I guess we could have done decimals with the 1/8.
Is it 8 or is it 4?
Oh, yeah, I was thinking 8 golf balls, but thank you, Jack. Oh, that would have been embarrassing. Actually, it already was kind of embarrassing. So yeah, it ends at 4. Thank you. The eighth golf ball is 4. All right, and then number 2, just write the word same. In order to calculate delta W, in order to calculate W sub I, which is delta X, it's just the same calculation. Okay, now let's go back to the left-hand Riemann sum, unless there's any question. Any questions on how to draw the diagram for left midpoint and right-hand Riemann sum? This goes deep in terms of concept development. There's a lot we're going to be able to build off of this. Okay, now for section 3. We're back on the left-hand Riemann sum, section 3. Here's what we write. Let capital A represent the signed area. Okay? Now, signed area is something you've never encountered before. In the past, in geometry, you've just had area. Area is never negative. Signed area can be negative. Signed area is a vector quantity. It has both magnitude and direction. So area above a curve is positively signed. Area below a curve is negatively signed. It's just because velocity, think about it in a total distance problem. Gotta watch out because sometimes people are on their way to work. It's like, oh, I forgot my wallet. I've got to stop and go home. Their velocity becomes negative. They start subtracting away from their total distance. So we're going to have positive area and negative area representing positive distance, which is distance going towards work, and negative distance, which is distance moving away from work. So it's a new concept called signed area. There is area in calculus that can be negative, that has a negative sign. So we're going to let A represent signed area. It turns out that the exact value of the total distance traveled, which is also in this case total displacement because the velocity is never negative, is the definite integral. So far we've been doing indefinite integrals with no numbers. So the definite integral from 2 to 4. We're starting at time 2, at x equals 2, we're ending at 4. So for the first time we're putting limits of integration on our integral of f of x dx. F of x is the square root of x plus 3. And this looks like area, doesn't it? It looks like length times width. It is area. There's a connection between this symbol and a limit of a Riemann sum because we're going to take the number of rectangles and go to infinity. It turns out that by definition, a definite integral is simply a limit of a Riemann sum. It's the limit as the number of rectangles goes to infinity. Because when the number of rectangles goes to infinity, the area, the overhang, goes to 0. And you get the exact total distance traveled, which is what problem 6 on that AP problem that we stopped at 5. But if we would have gone number 6, you would have needed a definite integral to solve it. So today we're learning how to do problem 6 on that AP test. So here's what you have to write. This is what we really mean. And by the way, I want you to know how to type this into your calculator because this is the exact answer. On your calculator, just pull it up, just so we have it there on the calculator. We're not even going to write it down yet. I just want it to be in your calculator. But to get this thing in your calculator, there's 2 things I want you to do. Not only do I want you to go to classic mode, but also turn your stat wizard off. Those 2 things are going to make today, we're all going to be unified on the same page. If you go classic and stat wizard off. Man. Okay. Now the calculator does its own approximations, but the best the calculator can do is on the home screen, unless you get a TI-89 titanium, but on the home screen with the TI-84, the best it can do to get the value of this expression, the actual total distance traveled, is on Math 9. So please go to Math 9. Math 8 was numeric derivative. Math 9 is finite integral. So whenever you see a definite integral that is an integral with numbers on it, you can evaluate it using finite integral. You need 4 arguments. First of all, you need the function. Let's just type in the square root of x plus 3. You need to type in the function. Comma. Second, you need to type in the variable. May seem kind of obvious, but it's like the variable is x. And then we have to give it the lower limit of summation, or basically the lower limit of integration is what it's called, comma, the upper limit of integration. So if you took the limit as the number of rectangles went to infinity, this would be the Riemann sum 9.4477 miles. Let's leave it on the calculator as a reference point, because when we do our Riemann sums, we're going to compare them to 9.4477 to see if the Riemann sums are too high or too low. It looks like from our pictures, the three pictures that you've drawn so far, it looks like the left-hand Riemann sum will be less than 9.4477. It looks like the midpoint Riemann sum, whoops, I see exactly what I did. I need to delete this empty page, that one right there. And might as well delete this empty page also. All right, so that's a midpoint. I think midpoint's gonna be pretty close. The left-hand Riemann sum will be too low. Midpoint will be pretty close. The right-hand Riemann sum will be bigger than 9.4477. But we're gonna put these Riemann sums on the calculator. So in the next 17 minutes, you're gonna learn how to get Riemann sums onto a calculator. The areas of all 8 rectangles onto your calculator. Ginormous concept development, starting with the left. So on your left-hand Riemann sum, we did section 3, which, by the way, section 3 is not done yet. You need to know that the exact area, keep forgetting what it is, 9.4477. You'd think I'd be able to remember that. That 9.4477 can be approximated by a Riemann sum. And the way we write out the Riemann sum is the summation from I equals 1 to 8. Why 8? Because we have 8 rectangles. We're going to add up L sub I times W sub I, the ith length times the ith width, where I goes from 1 to 8. That's how you can approximate a definite integral. We're going to fit this to height. I'm going to shrink a little bit on this so that I can draw more going on down. Okay. So but your paper still looks roughly like this. We're still in section 3. Definite integral gives me the exact answer. 8 rectangles gives me a pretty good approximation of the answer. Now, let's develop this concept a little bit further. The signed area is the summation from I equals 1 to 8. The ith length, that's F of golf ball C sub I. F of the ith golf ball, C sub I, times W sub I is going to be represented by delta X. That delta X calculation, which was B minus A over N, that's where we get, oh my goodness, this is looking just like that. S, sigma. That's no accidents. F of X, F of C sub I, dx delta X. This is coming together. Now, that completes step 3. By the way, in the center column, step 3, just write same. No changes. In the right-hand column, for section 3, just write the word same. There's no difference. This analysis is the same whether it's the left-hand, midpoint, or right-hand Riemann sum. Now let's go to step 4. The theme of step 4 is no sigma. We want to ditch the sigma in step 4. The way to ditch the sigma in step 4 is to declare, and here we're on the left, A equals, I think that when we put a 1 in for I, we get F of C1 times delta X. And would you use your imagination here for a second? I'm going to write out 8 terms. Want it be F of C1 times delta X plus F of C2 times delta X plus F of C3 times delta X plus dot, 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 all the way up to F of C8 times delta X. Notice how all 8 terms have a delta X. Are you okay with me just factoring out the delta x, so I have to write delta x only once? Is that okay with you? All right, so this is gonna be A is approximately equal to delta x times f of C1 plus f of C2 plus dot 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 plus f of C sub 8. I did it, I got rid of the sigma. And that is going to be the same. Step 4 is identical. So you just write the word same for midpoint and for right-hand Riemann sum. No difference there. Step 5. The theme of step 5 is no more f's. Let's get rid of the f's in step 5. Careful concept development here. So in step 5, I've got A is approximately equal to delta x times the square root of C1 plus 3 plus the square root of C2 plus 3, because isn't f of C sub or C1 the square root of C1 plus 3? And f of C2 is the square root of C2 plus 3 plus dot 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 plus the square root of C8 plus 3, close parentheses. Any questions on step 5? You're wondering how many steps there's only 7 steps. We're all the way up to 5, and guess what? Step 5, you don't have to redo it in the middle and on the right, because it's identical. It's the same for midpoint Riemann sums, and it's the same on the right. Now, once we hit step 6, then it's going to be different. And I'm actually out of paper here, so it's not really paper, but I think of it as paper. So step 6, the theme of step 6, which is going to be different across the 3. So this one we're going to have to do 3 times. Is everyone okay? How about in 12 minutes, let's just take a break. In fact, we can even leave the room. Go grab some food in 12 minutes, okay? So the theme of step 6 is there's 3 things we're going to ditch. Actually, just 2 things. We're going to have no more C sub i's and no more delta x. So in step 6, we write the signed area is approximately equal to delta x was 1/8 times, and now we have to go back to step 1 and look at what were our C sub i's. So it's going to be square root of, what was the first golf ball in the left-hand Riemann sum? I believe it was a 2 plus 3 plus, what was the second golf ball? Second golf ball, wasn't it 2 1/8? Is that 2.125? 2.125 plus 3, comma. I'm sorry, what's that?
Here's the point. Yeah.
2.5.
It's 1/4.
It's 1/4, 2.25.
Yeah, sorry, I should have confused you on that. Oh yeah, it was just 2.25. I was thinking midpoint already. And so thank you for keeping me from going too far astray. So that's the square root of 2.25 plus 3, comma, dot, 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 plus the square root of 3.75 plus 3. Shriana, you had your hand up.
So for delta x, that's the width of the rectangles, right?
That all 8 rectangles have the width of, yeah, it's the width.
Isn't it 1?
Oh, okay. So, and Shriana has, see, I guess I'm the one who needs a break, because she's absolutely right. Each rectangle was 1/4 wide, so, and you caught that right away. Thanks. Wow. I'm so glad you're on top of this. Isn't delta x 1/4? We calculated that up in step 2. So thanks for hitting that one. Now, what we do in step 7 is we type this into the calculator. We type in the sum of a sequence, because I don't know if you're aware of this, but a series is the sum of the terms in a sequence. And in our calculators, we're going to type in sum of a sequence square root of x plus 3, comma, x, comma, the first golf ball is 2, the last golf ball is 3.75, and the distance from one golf ball to the next is 0.25. And that's gonna give us the area of all 8 rectangles. So let me show you how to type that in. You may have never gone to this part of your calculator before, but when you want to add up a list of numbers, Jack, do you have a question?
Oh yeah, what do we do for 6 for the middle?
Oh yeah, so, you know what, we're doing 6 and 7 together. Let's do 6 and 7 together. So, class, take out your calculator. For the first time in your life, well, it might be the first time in your life, I'd like you to go to the list menu, because we have to add up a list of 8 numbers. So I hit second list, and arrow to the math submenu. Math submenu. Item 5 is a sum. We want to take the sum of a sequence. Now go to list again, but this time go to the ops submenu to get sequence, which is item 5. We want to find the sum of a sequence where, oh my goodness, I can't believe this. I should have inserted delta x out front, which is 0.25. So, because it's 1/4 times the sum of a sequence. So there's the widths, and now we're going to add up the 8 lengths. So it's 0.25. Just to emphasize this is 0.25 times, and here's how we can most efficiently type in all 8 numbers. On the homework, it's going to be 32 numbers, but you can do it efficiently using some sequence by typing in the square root of x, close the parentheses, plus 3, comma, the second argument is x, comma, the third argument is the first golf ball, which was 2. The fourth argument is the 8th golf ball, which is, doing it in my head, 3.75, comma, and the 5th and final argument is the distance between the golf balls, which is 0.25. Now this is, notice it's less than. This is what we expected. We expected it to be less than the truth. It's 9.3739. So that's the answer to the first column. Your left-hand Riemann sum is 9.37395. Now let's complete the middle column. Will, go ahead.
So why is there 0.25 in front?
Oh, because it's this 0.25. Okay, so you know what? I could make this a equals 1/4 times the sum of the sequence. I was just focusing on this stuff here, but this sequence, we want to sum up this sequence. It has 8 terms, starting at 2, ending at 3.75, but it's really all being multiplied by 0.25. We're trying to add up the areas of all 8 rectangles. We don't want to just add up their lengths. We want to add up their length times widths. Now, let's go to the middle column. And fortunately, we can copy and paste on the calculator because, oh, by the way, in the middle column, so in the midpoint column, step 6 is going to be a is approximately 1/4 times the square root of, and this is the one that was 2 1/8, which is 2.125. Am I doing my fraction work correctly? Plus 3. Plus, the second golf ball is at a height of the square root of 2 points. You know what? Honestly, what I do, I usually don't deal with decimals here. If it is just less time, I have no problem going like this. Square root of 2 and 1/8, because we listed them down up in section 1. We had 2 plus 1/8. And the next thing we had 2 plus 3/8 plus 3 plus dot 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 plus. And then we did square root of 4 minus 1/8 and then plus 3. And this is actually, because you don't really want to mess with decimals. It's better with Riemann sums to work with fractions. So on the calculator, especially when the decimals go forever. So just do the fractions. So watch this, press second enter, it comes up, let's just go and edit this. All that's the same. The first golf ball is, I'm going to delete all this out. Watch how easy it is to type in. I'm just going to type in 2 plus 1/8 is the first golf ball, comma. The last golf ball is 4 minus 1/8, comma, and the distance between the golf balls is 1/4. It's by far the fastest way to type in the midpoint Riemann sum. First golf ball, which is listed up there in part one. The last golf ball is listed up there in part one. For your benefit, 4 minus 1/8. And the distance between the golf balls is 1/4. We're expecting this one to be pretty close to the truth. And look at that, 0.447, so 80. Wow, that's really close. The midpoint Riemann sum is the boss. Now see if you can do the right-hand Riemann sum on your own, and then I'll tell you what the homework is. So do section 6 and 7 of the right-hand Riemann sum. All right, what was it, 2 1/4, 2.5, 2.75, plus. And then, oh, right-hand Riemann sums, that's nice, it just goes square root of 4, plus 3. Oh, by the way, yeah, I mean, you're not really done with these columns until you say A is approximately, and then copy down the decimals from your calculator. So on this one, press second entry, most of it's typed in. All you have to do is say the first golf ball is now 2 plus 1/4. Look, I'm just overstriking a few things. The last golf ball is 4, and the distance between the golf balls is still 1/4. These go really fast if you just do second entry to bring up the previous one. So that's my right-hand Riemann sum, which, as you can see, 9.4, it's way too big. It's an overestimate, but you knew it was going to be an overestimate because the rectangles were hanging out above. Now, here's your homework. Your homework is to do a full sheet of paper, do a left, a midpoint, and a right-hand Riemann sum with a different function. And we're calling it homework 4.4. So here's homework 4.4, which is due tomorrow. Paper submission. This time the function is going to be f of x equals, and it's natural log x multiplied by, in my 4th period class, I gave them x squared. It's going to get pretty high, but okay, x squared. We're going to go from 3 to 25. So instead of from 2 to 4, we're going from 3 to 25 with n equals 32 rectangles. So instead of 8 rectangles, it's 32 rectangles. Round your answers for the left, midpoint, and right-hand Riemann sum to go at, with 32 rectangles. You should be able to get them to 3 decimal places. So round your 3 answers to 3 decimal places. That's a homework. It's due tomorrow. You are dismissed.